All right, this is 2.8 video 3. We are right into the thick of it now. So example number 6. A spherical balloon is inflating at a rate of 60 pi inches cubed per second. Inches cubed per second, that's a volume change. So let's go ahead and write that one down. dV over dt is 60 pi inches cubed per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? Well, they gave us the when, 4 inches, radius is 4 inches. They want to know how fast the surface area of the balloon is expanding. So we want to know what the change of the surface area of the balloon is over time. Nicely, they gave us a couple of equations here. We're going to have the volume equation and the surface area equation. So we're looking for how the surface area is changing. So let's start off with that one. We're going to start off with the surface area being 4 pi r squared. Okay, let's take the derivative of that to see what pieces we need. So the derivative of the surface area is the derivative of surface area with respect to time. And then the right side, we'll bring the 2 from the r out front. We're going to get 8 pi r, and don't forget the radius is changing, so it's dr over dt. So now let's see what information we have. We have the radius, that was 4. We need dr dt. I don't have that anywhere. They didn't tell me how the radius was changing. But they did tell me how the volume was changing, and the volume is related to the radius. So we can set up a separate equation of the volume. And if I were to take the derivative here, I would get dv over dt. That's good because they gave me something with that. Bringing the 3 out in front and multiplying it by the 4/3 gives us 4 pi r squared dr over dt. And the nice thing is here, I can solve for dr over dt at exactly the same time because I can plug the r equals 4 into this right here, and I've got dv over dt. So I can solve for dr over dt at exactly that same moment in time. So let's go ahead and solve for that. dv over dt is given to us as 60 pi equals 4 pi. The radius was 4 dr over dt. And this one did not say approximate, so we're going to leave pi in terms of pi. The nice thing here is that the pi's are going to cancel out when you divide them out of each side. On the right side, I'm going to have 4 squared, which is 16, times 4 more is 64. So I have to divide 64 on both sides, which is going to give me 60 over 64 equals dr over dt. 60 over 64 does reduce. 4 goes into both of them, so it's going to be 15 over 16. So there's my dr dt. So now I have the radius, I have dr dt, which is what I'm going to need to complete finding dsa dt. It's going to be 8 pi times the radius, which was 4, times dr over dt, which is 15 over 16. All right, let's practice a little mental math here because this is something that you should be able to do without writing everything out. In general, it is always good to make things smaller before you make them bigger. In this case, what I can see is that I've got an 8 times 4. Well, that's 32. Then I'm going to divide that by the 16. 32 divided by 16 is 2. Then I'm going to multiply that by the 15. So 2 times 15 is 30. So ultimately what we get here is 30 pi. Okay, you can do that. Find things that make it easier to multiply and divide. 30 pi, and this is how area is changing. It's surface area. So it should be some kind of unit squared per time. And the units were in inches, so it's going to be inches squared per, what was it, second. So the surface area is changing at a rate of 30 pi inches squared per second, specifically when the radius is 4 inches. So in this case, we actually needed a secondary equation to be able to find some of the missing pieces that we had to have for the first equation or for the primary. Okay, oil is spilled from a tanker. It's spreading in a circle whose circumference increases at a rate of 40 feet per second. Okay, so that automatically tells us dc over dt is 40 feet per second. How fast is the area of the spill increasing when the circumference is 100 pi feet? So they're telling us the circumference is 100 pi feet. We want to know how fast the area is changing, so that's going to be dA over dt. And it's the circle, which is really nice that the oil is spreading in a nice perfect circle for us. Okay, so let's see. We want to know how fast the area is changing. Area of a circle is never going to be given to you. You must know this one. Area of a circle is pi r squared. So we're going to start off with area equals pi r squared. Take a derivative, see what we need. So the derivative of A is dA over dt. The right side will bring the 2 out to the front. So 2 pi r dr over dt. Well, they didn't actually give us the radius. They didn't give us how the radius is changing. That's not helpful. But what they did give us was something about how the circumference is changing. Well, I do know something about the circumference of a circle. I know that the circumference of a circle is 2 pi r. So now if I were to take the derivative of that to get a dc dt, that's good because I have that information. The derivative of the right side is just going to be 2 pi times dr over dt. Okay, well, good. I know how the circumference is changing. That's 100 pi equals 2 pi times dr over dt. Dividing both sides by 2 pi is going to give me 50. That is dr over dt. Okay, so at least I have that information now. So I know that dA over dt is going to be 2 pi. I don't yet have r. I can find it, but I don't have it. Times 50. That's the dr over dt. So we're going to leave a space there for the radius. Well, I know that the circumference formula is 2 pi r. I know that my circumference is 100 pi. So that's got to equal 2 pi r, which means that my radius is 50. So something is wrong. What did we do? Oh, I see it. Okay. All right. My dr dt is wrong. The radius is correct. So we're just going to switch this. Try to there. We're going to switch that. That's the radius. Dr dt is incorrect. Hopefully you guys caught that. I plugged in 100 pi. I plugged in the circumference. dc over dt is actually 40. That makes a huge difference. So now if we divide that by 2 pi, we're actually going to get 40 over 2 pi, which reduces to 20 over pi. Okay, that makes a big difference. So now we're going to plug in 20 over pi for dr dt. Hopefully you guys caught that. So dA over dt is going to be, let's see, the pi's are going to cancel out. I'm going to get 2 times 50, which is 100. Multiplying something by 100 really adds 2 zeros to it. So 20 times 100 is going to be 2,000. So we're going to get 2,000. It's how area is changing. So it's going to be something squared, feet squared per second. So the rate of change of that oil spill is 2,000 feet squared per second. All right, moving on. Car A and B leave town at the same time. Oh boy, here we go. Everybody's favorite type of problem. Car A and B leave town at the same time. Car A who heads due south at 80 kilometers per hour. So 80 kilometers per hour that way. Car B heads west. That's this way. At 60 kilometers per hour. Kilometers per hour. How fast is the distance between the cars increasing after 3 hours? So we are looking to see how fast this distance here between these two cars is increasing after 3 hours. So I know the time is 3 hours. Let's see, what were we given? We were given dx dt and dy dt because that's the horizontal and vertical directions of a right triangle here. So we were given that dx dt is 60 kilometers per hour and dy over dt is 80 kilometers per hour. We are trying to find how fast the distance between the cars is changing, so that would be dz dt in this case. All right, so this looks like a Pythagorean theorem type problem because it's got x, y, and z, and it's got a right triangle. So let's start off with that. So we've got x squared plus y squared equals z squared. The derivative, 2x dx over dt plus 2y dy over dt plus, equals 2z dz over dt. And just like before, the nice thing is that we can divide the 2 out, so we don't have to worry about the 2. You can leave it in if you want. It's just going to make your numbers much bigger to deal with. So let's see what we have. Well, we've got dx dt. We can fill that in. That's 60. We've got dy dt. That's 80. We need to find dz dt. That's what we're looking for. What we don't have is x, y, or z, but we do know the time traveled. Okay, so we know that these cars traveled for 3 hours. So 60 kilometers for 3 hours, 60 kilometers per hour, for 3 hours is going to be 180 kilometers. So that's going to be 180 in the x direction. In the y direction, it's going to be 3 times 80, which is 240. So that's going to be 240 here. And then using some Pythagorean theorem, again, I'm not going to go ahead and show all this, but you would end up getting 300 right here. That's how far they are apart, but we want to know how fast that distance is changing when they're that far apart. So it's going to be some pretty big numbers here, but ultimately we can now go ahead and solve for dz over dt. So we're going to get 180 times 60 plus 240 times 80, all divided by 300. And that'll be dz over dt. All right, that's going to be pretty big numbers, but ironically, it works out pretty nicely. It's going to end up being 100 kilometers per hour. That's your dz over dt. Now, if you've taken physics, you might have already known there was a slight shortcut to this. You really could have just done the Pythagorean theorem of the rates of change. So if you had done Pythagorean theorem with the 60 and the 80, you would have gotten 100. Only works when the cars are starting exactly the same point and heading off in perpendicular directions. All right, let's move on to the next one. A cylindrical tank with a radius of 6 meters is filling with fluid at a rate of 100 pi meters cubed per second. 100 pi meters cubed, three-dimensional, that's volume. So dV over dt is going to be 108 pi meters cubed per second. How fast is the height increasing? So we're trying to find dH over dt, specifically when the radius is 6 meters. Okay, so here's the good thing. This is a cylinder. A cylinder, the radius doesn't change. So we know the volume of a cylinder. We did talk about that. The volume of the cylinder is going to be pi r squared h. But the radius is constant because it's a cylinder. It doesn't matter how fast you put fluid in or take fluid out of a cylinder, the radius doesn't change. So we can fill in the 6 right away. It's going to be pi times 6 squared h. Now the height is changing because we're filling the cylinder with fluid. The volume is changing because we're filling it with fluid. So now we can go ahead and take the derivative. So we're going to get that dV over dt is going to be, let's see, that's going to be 36 pi, just simplifying that. The derivative of h is dH dt, which is what we're looking for. So now all I have to do is fill in the dV over dt, which is 108 pi. And now we can solve for dH over dt. Whoops. So dividing both sides by 36 pi, 108 divided by 36 actually works out very nicely. That's going to give us 3. So our dH over dt is 3, and I should have left myself some room. Its height, it's linear, so it's just going to be meters cubed. I'm sorry, meters per second. Okay, singular, just meters per second. All right, getting close. Okay, this one's going to be a little bit more involved because most of us don't remember the formulas for this. The sides of an equilateral triangle are increasing at a rate of 27 inches per second. How fast is the triangle's area increasing when the sides of the triangle are 18 inches long? All right, so it says when the side is 18 inches long. It's supposed to be an S, side. Okay, we want to know how fast the area is increasing, so we want to know dA over dt. And it says that the side is increasing at 27 inches per second. So the side, ds over dt is going to be 27 inches per second. All right, so the problem is most of us know the area of a right triangle, but this is an area of an equilateral triangle. A little bit different. So if I can kind of draw it, it's supposed to be equilateral. That does not look equilateral at all. Try again. Whoops. All right, that's much better. Okay, so we know that each side is 18. So okay, each side here is 18. It's telling me that the sides are increasing at 27 inches per second. Okay, that's not a problem. I need to come up with a formula here to actually find the area. Again, we know that the area of a triangle is 1/2 base times height. Problem is, I can give you the base. That's no problem. The height itself is the harder part to find. We want to come up with all of these base and heights in terms of one variable if possible. So we don't have to worry about some kind of a product rule here. So I want to write the base in terms of a variable. Well, I've got that S is the base. So it's going to be 1/2 S because that's one of the sides. The height is a different story. The height is measured from the vertex perpendicular. Whoops, keep hitting the erase button, unfortunately. The height is perpendicular from the vertex of the other side. So what that does is it takes an equilateral triangle where all the angles were 60 degrees and splits the top one into a 30-degree angle. Well, this one down here is still 60, and the nice part about that is it creates a 30, 60, 90 right triangle. And I know some properties about that. Well, I've given me the hypotenuse, which is 18. Okay, that's this side over here. That's the 18. I know that the short side of a 30, 60, 90 is half of the hypotenuse, which makes sense. That would be 9 because it's half of the other side of the equilateral triangle. But even more importantly, I know that the other side is going to be the short side times the square root of 3. So the length of this thing would actually be 9 squared 3. Now that's not really that important. What is important is that in general, this is going to be 1/2 of the side, which means that the vertical piece or the height of this triangle is going to be 1/2 that side times the square root of 3, or square root of 3 over 2 S. Okay, that's the height of the triangle. So I'm going to fill that in as the square root of 3 over 2 S. Now I can go ahead and, well, I'm going to simplify first, but we can take derivatives because I know how the side is changing. And I'm trying to figure out how the area is changing. So we have everything we need. So let's simplify this. So 1/2 times square root of 3 over 2 is going to be the square root of 3 over 4. And S times S is S squared. Now we can take a derivative. Area is changing over time. Taking the derivative, we're going to get 2 times square root of 3 over 4, which is going to be the square root of 3 over 2 S ds over dt. And the good thing is, I know what ds over dt is. They gave it to me. I know what the side is. They gave it to me. So now we can find dA over dt. So square root of 3 over 2. The side is 18. ds over dt is 27. So simplifying that, let's see, 18 over 2 is 9. 9 times 27, not as easy to do that one mentally. It's the same thing as 27 times 3 times 3 more. 27 times 3 is 81. Times 3 more is 243. So we're going to get 243 square root of 3. And it is how area is changing. So that'll be inches squared per, what was this, second. So the area is changing at 243 square root of 3 inches squared per second. All right, there is one more problem on there. It's another one of those inverted conical containers or inverted cones. It's just got some different information. I'm actually going to leave that one. I'm not going to do that one in a video. I'm going to leave that one for you guys to figure out. I can tell you that the answer to this one should be negative 5/7 inches per second. So see if you can match that answer and get the actual problem. It's a good practice problem for you to do. All right, plenty enough for all the videos.